Joey, can quantum mechanics actually break time? We think of time as a simple straight line, a fundamental rule of the universe that flows in one direction, from past to future. An egg shatters, it never unshatters. We have memories of yesterday, but not of tomorrow. But what if that's not the full story? What if, at the deepest level of reality, time isn't a one-way street? What if it can be bent, twisted, and maybe, just maybe, reversed? And no, this isn't science fiction. This is the strange reality of our most successful theory of the universe, quantum mechanics. The quantum world is bizarre. It's a place where particles can be in many places at once, where simply looking at something can change it, and where two particles can be mysteriously linked across the entire cosmos. It's a place that seems to delight in breaking our common sense. So, what happens when this weird, microscopic world crashes into our basic idea of time? The results challenge everything we think we know. They hint that time travel might not be so impossible after all, but in a way you'd never expect. And it forces us to ask an even bigger question: is time even real? Section 1. The Arrow of Time. Before we get into the quantum weirdness, let's start with something we all experience: the arrow of time. You spill your coffee and it makes a mess. You see a building fall, but you'll never see a pile of rubble spontaneously become a skyscraper. Physicists explain this one-way street using a crucial law of nature, the second law of thermodynamics. It basically says that in any closed-off system, things always get more disordered. This measure of disorder is called entropy. A perfect sandcastle is eventually worn down into a messy pile of sand. The universe itself is moving from a state of low entropy to high entropy, and this relentless march towards disorder is what gives time its forward direction. It's why the past and future are different. For more than a century, this was the story of time, simple and irreversible. But this neat picture unravels when you look really, really closely. The fundamental laws of physics that control individual particles are mostly time-symmetric. They work perfectly forwards or backwards. A video of two billiard balls hitting each other looks normal, whether you play it forwards or in reverse. So if the tiny fundamental laws don't care about which way time flows, where does our arrow of time come from? That's one of the biggest mysteries in physics, and the answer might be hiding in the quantum world. Section 2. Quantum time travel and the grandfather paradox. So let's go straight to the wildest idea: breaking time by traveling through it. This isn't just a fantasy. Einstein's theory of general relativity says that massive objects can warp space-time. In some extreme cases, space-time could bend so much that it creates a closed time-like curve, or CTC. Think of it as a path through space-time that loops back on itself, which could theoretically let a particle or a person travel to their own past. But this immediately leads to the most famous problem in time travel: the grandfather paradox. What if you travel back in time and stop your grandparents from ever meeting? If they don't meet, you're never born. But if you're never born, you couldn't have gone back to stop them. It's a brain-breaking logic loop that seems to make time travel impossible. For a long time, this paradox was a major argument against CTCs. Stephen Hawking even came up with a chronology protection conjecture, suggesting that the laws of physics must have some rule to prevent time travel and its messy paradoxes. But what if the same bizarre laws that seem to cause the paradox also offer a solution? What if quantum mechanics has an escape hatch? Section 3. The quantum resolution. This is where the quantum world steps in. When physicists started modeling what would happen if a quantum particle, like a photon, went into one of these time loops, they found something amazing. The rules of quantum mechanics seem to have a built-in paradox defense system. An early idea is the Novikov self-consistency principle, which says that anything a time traveler does in the past must be part of a self-consistent history. In other words, the laws of physics would stop you from creating a paradox. Maybe your weapon jams, or you slip on a banana peel at the last second. You can be part of the past, but you can't change it. More recent quantum theories take this even further. Some models suggest that when a particle enters a time loop, it exists in a superposition of states, both succeeding and failing at its paradoxical mission. When it comes out, only the outcomes that make logical sense survive. Quantum simulations have actually shown particles navigating these time loops, and they consistently find that quantum mechanics uses its built-in weirdness, like entanglement and superposition, to clean up any paradoxes. One incredible theory from Dr. Lorenzo Gavasino proposes that thermodynamics itself might work differently inside a time loop. As something travels along the loop, its entropy could reverse, essentially wiping any memories or intentions to cause a paradox by the time the loop is finished. So, quantum mechanics might not forbid traveling to the past, but it does seem to make it impossible to mess with it. You could be a tourist in your own history, but you could never be a vandal. Section 4. Is time even real? The emergent time theory. But what if the real reason we can't seem to break time is because, on a fundamental level, there's no time to break? This is probably the most mind-bending idea in all of physics. The theory that time isn't fundamental at all, that it's an illusion, an emergent property that arises from something deeper. And that deeper thing? Quantum entanglement. Entanglement is the spooky action at a distance that bugged Einstein, where two particles become so deeply linked that their fates are tied together, no matter how much space is between them. Back in the 1980s, physicists Don Page and William Wooters proposed a wild idea called the Page-Wooters mechanism. They suggested that if you could somehow look at the entire universe from the outside, you'd see a completely static, timeless state, a frozen photograph. In this view, time only emerges when you look at the relationship, the entanglement, between one part of the universe and another part that acts as a clock. Imagine a static picture with two entangled coins. If you just look at one, it's just a coin. But if you notice that every time one is heads, the other is tails, you perceive a connection, a sequence. According to this theory, time is that sequence. It's the correlation between a system and a clock. For anything not entangled, time wouldn't exist. The universe would be frozen. This isn't just a philosophical idea. In 2013, an experiment actually demonstrated the Page-Wooters mechanism using entangled photons. From an outside perspective, the photons were in a static state. But when one photon was used as a clock for the other, the second photon appeared to evolve. Time emerged right there in the lab. If this is right, our feeling of time's flow is just a product of our own quantum entanglement with everything else. Time isn't some absolute river. It's a story our minds create from the quantum connections that hold reality together. Section 5. The ultimate clash. Quantum versus relativity. This all leads to the biggest headache in modern physics, the problem of time. Our two great theories of the universe, general relativity and quantum mechanics, treat time in ways that are completely at odds with each other. In general relativity, time is relative and dynamic, woven into space to create the stretchy fabric of space-time that gravity can bend. But in quantum mechanics, time is an outsider. It's a rigid, universal clock that just ticks along, unaffected by all the quantum weirdness it's supposed to be measuring. This deep disagreement is the huge wall blocking a unified theory of everything. How can time be both flexible and fixed, relative and absolute? Trying to solve this has pushed physicists into even stranger territory. Some attempts to merge the two theories, like the famous Wheeler-DeWitt equation, end up with time just disappearing from the math completely. The equation that tries to describe the entire quantum universe has no time variable in it, which supports the idea that time is just an emergent illusion. Figuring this out is the ultimate goal of physics, and it might mean we have to throw away our most basic intuition about time and accept that it's just a side effect of deeper quantum processes. This dive into the quantum nature of time takes us right to the edge of what we know about reality. We've seen how quantum rules might allow for time loops while preventing messy paradoxes, and how time itself might just be a shadow cast by quantum entanglement. So, what do you think is going on? Is time a real, fundamental part of the universe, or is it the most convincing illusion we've ever known? Drop your theories in the comments below. And if you love thinking about the biggest questions in science, make sure to subscribe and hit that notification bell so you don't miss our next trip into the unknown. Conclusion. So, can quantum mechanics actually break time? The answer seems to be a frustrating and fascinating yes and no. It doesn't look like it allows for the blockbuster movie kind of time travel, where you can rewrite history. Instead, it offers a beautifully strange system where the past is safe from meddling. But on a deeper level, quantum mechanics might do something even more radical than breaking time. It might get rid of it completely. The theories of emergent time suggest that the steady flow we feel every day is a grand illusion, something our brains build from a timeless, deeply interconnected quantum reality. Maybe we aren't just passengers floating down a river of time. Maybe we're all participants in a silent cosmic dance of quantum information. The true nature of time is still one of the greatest unsolved mysteries, a puzzle that shows us that the universe is far stranger and far more beautiful than we can even begin to imagine.